Hello, everybody. Welcome. Thank you for joining us today. You are part of the 240 people worldwide who have registered to this webcast powered by Yole Développement and System Plus Consulting and supported by the China International Optoelectronics Exposition, CIOE. This webcast will deal with ADAS, Advanced Driver Assistance System for Automotive. My name is Faisal Kamasi. I am Global Sales Support and Coordination Manager for Yole Développement. To shortly introduce you to the two companies, Yole Développement and System Plus Consulting are part of the Yole group of companies which providing marketing, technology and strategy consulting, media in additional to corporate finance services. We support industrial companies, investors, and R&D organizations worldwide to help them understanding markets and follows technology trends to develop their business. Before we start this webcast, let me just give you some basic information on this online event. You have the possibility to submit questions during all the webcasts. You can use the Ask a Question window at the bottom of the screen. We will answer as many questions today as we can, and for the remaining one, we will follow up with you via email. We'll do our best to do that. Concerning the material, please note that this presentation are already available and they can be downloaded from the resources section of the platform. Furthermore, you will receive tomorrow an email with the link to the recorded webcast session. So let's start the webcast. I'm pleased to welcome Pierrick Boulet, Market and Technology Analyst at Yole and specialist of the solid-state lighting industry, and also Wilfried Theron, Electronic System Department Director at System Plus Consulting. So let's begin with you, Pierrick.
Hello, thank you, Faisal, for the introduction. Hello, everyone. I am Pierrick Boulet, analyst at Yole Développement. So during this webcast, I will briefly introduce the megatrends and the context related to ADAS vehicles. Then I will talk about sensors for ADAS and how the electronic architecture and computing is expected to evolve. And then I will continue by giving some insight on the related industry and market forecast. So on the next slide, you see the introduction. You see the acronym, the CASE acronym, taking over the auto industry. So the CASE acronym stands for connectivity with comfort, safety, and entertainment, taking more place in ADAS vehicles. The second megatrend is autonomous, because more and more sensors are integrated into ADAS vehicles with more computing to increase the safety and develop automated driving features. The third megatrend is linked to shared habits. So this is related to the new mobility with owning, sharing, or renting vehicles, and it will offer greater flexibility in the future. The last one is related to electric and the electrification of vehicles. So OEM have to reduce the CO2 emission. And if they don't, they will have some penalties related to the CO2 emissions. So this is also a very important topic for OEMs as well as the development of autonomous features. On the next slide, on slide 7, you see that the recent news related to ADAS, so it's acquisition, partnership, or fundraising that have been made regarding ADAS and autonomous driving. This is related to camera, radar, LiDAR, and computing. And you see that many players are developing partnership or acquiring other players, and you see that it's very active, and it is expected to continue in the next years. So on slide 8, you see that the ADAS is driven by safety, and one important safety feature is the AEB system. And here that you see that the volume and the penetration rate of AEB system is continuously increasing. So it started so in 2017, the penetration rate was about 18%. And in 2019, it increased to 38%. So it's a very rapid increase of the AEB feature. As of today, the AEB system rely mostly on the forward camera and the long-range radar. But this AEB system can be improved because these systems have some difficulty in low light conditions, and adding some sensors like LiDAR or thermal camera could improve the performance in such conditions. But this will require more sensors and therefore more computing. So in slide 9, in ADAS vehicles, so you see that there are a lot of sensors that are embedded. So you can find some ultrasonic sensors, cameras on the front, on the rear side, but also short-range radar or long-range radar. And even LiDAR for some cars. So this means that more ECUs will be requested, more computing power, and therefore more software will be requested to process all the data, and a more complex electronic architecture will be needed in vehicles. On slide 10, you see the actual electronic architecture that can be found in ADAS vehicles. So it's a distributed architecture with basically $30 to $150 ECUs can be found in vehicles. On the right hand side, you can see a typical network that is used in vehicles. So you have a central gateway with different networks. So you can find the CAN high-speed network for powertrain or chassis application, CAN low-speed for comfort application, LIN network for small sensor and actuator like the rain sensor or light sensor, the MOS network for all the multimedia application, and flexway network. So this is quite complex, and this is expected to change in the next years. On slide 11, you see the evolution of the electronic architecture. So this is a roadmap. So as of today, this is a distributed architecture. So the one function for one ECU principle is expected to evolve with the merging of some ECUs, but this will be limited to a few functions. Then we expect this architecture to evolve toward the domain centralization in 2025 with the creation of specific domain controllers. So 5 domain controllers for infotainment, comfort, powertrain, sensing, and safety. And here you see that the number of ECUs is expected to decrease, and we expect 30 to 60 ECUs. The last evolution could appear in 2030, 2035 with a complete vehicle centralization using some kind of supercomputer that gathering all domain controllers, but still use some ECUs for some few functions. And therefore, we expect 20 to 45 ECUs in total. On slide 12, so you see the impact of this change of architecture on the sensors. So as of today, some sensors still embed some IC for pre-processing. These type of sensors has a limited computing power. And it is quite difficult to fusion all the data coming from different sensors. So with the evolution of the electronic architecture, sensors will evolve from being smart sensors to dumb sensors, so without any processing, and they will send only raw data. So this will enable higher autonomy levels, but it will require a large bandwidth network and a high computing power to process all the data and fusion the data in low latency or in real time. On the next slide, slide 13, just to mention that the Ethernet network is coming and is one type of network that will enable to send all the data generated by sensors because the Ethernet network has a higher bandwidth compared to the classic networks that are today found in vehicles. And we expect that Ethernet will be more and more used in the next years. On slide 14, you see the architecture of the global view of the system. So you have the sense part that gather the data coming from the camera, the LiDAR, the radar, and the ultrasonic sensor. The raw data is sent to the computing unit, so our domain controller. And then this controller is processing all the data and will act on the different ECU for transmission, for the engine, the braking system, or the steering. And computing power will become more and more important. And the associated software for automatic driving will become a differentiating parameter for OEMs. So next slide, on slide 15, you see that the new electronic architecture will enable data fusion for automatic driving and therefore will enable new functions. So as of today, in 2020, there are limited number of functions, and it's using mainly the forward ADAS camera and radar. And as of today, only the ADAS camera is multi-purpose. But in the future, when we will see more centralized architecture as a domain of vehicle centralized architecture, more functionality will be developed, and they will use data coming from different sensors, and new sensors will be added for redundancy. So on the next slide, slide 16, you see that the electronic architecture is at the center of the case megatrend. So for the electrification, for example, you can see that some improvement can be made by new algorithm to have a better, let's say, energy management to reduce the consumption. It's the same on the connectivity with over-the-air updates or regular over-the-air updates. And on the autonomous driving system side, as more and more sensors will be integrated, it will require a new architecture, and it will demand for higher computing power and communication. And this will be also the same for shared mobility. And we see that the electronic architecture will be, let's say, an enabler for all these megatrends. On slide 17, you see the industry overview of ADAS sensor. So here I put the main industry related to camera, LiDAR, and radar. So the camera and radar industry are quite mature today, while the LiDAR industry is relatively new compared to the two others. We see that some big players are involved in the three industry, like Valeo, Continental, or ZF, for example. And we do see that for LiDAR, there are a lot of new players dedicated to this industry, and mainly startups. So on the camera industry, Denso and ZF are leaders with 19 and 80% market share. On the LiDAR industry, Valeo is today the only player, but this is expected to change with future entry of Innoviz with BMW and Luminar with Volvo. For the radar market, Continental and Denso are leaders with 25% and 16% market share respectively. And on the AEB computing hardware, this market is led by Mobileye with 53% market share in volume, followed by Xilinx with 20% market share. The next slide, slide 18, you see the supply chain of sensors used in the Audi A8. So these are the main sensors for the AD, the front ADAS camera, the long-range radar, and the LiDAR. So the LiDAR is supplied by Valeo, the long-range radar supplied by Bosch, and the front camera is supplied by Aptiv. And all these sensors, these three sensors, are directly linked to the zFAS domain controller, where all the processing is done. So you see that the Mobileye chip is not inside the camera module, but inside the domain controller. And it's the same for LiDAR and radar, and all the processing is done in the zFAS module. So I will conclude my talk on this slide to present you the global market for ADAS sensors and computing. So as of today, the global market represents $8.6 billion. This is expected to grow quite fast at 20% CAGR between 2020 and 2025. And in 2025, we expect that this market will reach $22.4 billion. And this market will still be driven by camera and radar, because they are the main sensors used in the AEB system. But you see that the LiDAR market is expected to grow very fast at 113% CAGR, which is normal because more OEMs are expected to integrate LiDAR in the next 5 years. So thank you for your attention. I will let now Wilfried continue for the second part of this podcast.
Thank you very much, Pierrick, for your very interesting presentation. Yes, as Pierrick mentioned, we will continue with Wilfried Théron, from System Plus Consulting, who will describe the solution from Tesla and Audi. So, Wilfried, the floor is yours.
Thank you, Fecal. This is the short agenda of my presentation. I will begin with a description of the ADAS sensors on the Tesla Model 3 and Audi A8 to see different architectures of these vehicles. Then I will go into more details concerning some camera modules, and to finish, I will do a comparison between the last two versions of the Tesla Autopilot ECU and the active zFAS ECU. On this slide, we can see the different ADAS sensors used on the Tesla Model 3. There are 8 cameras placed all around the car, and all these cameras are manufactured by Tesla. Only one radar from Continental in the front of the car, and there are also 12 ultrasonic sensors from Valeo. All these sensors enable safety features like lane and speed assist, collision avoidance assist, and also convenience features like traffic-aware cruise control, and of course the navigation and autopilot. These sensors are directly connected to only one computer unit manufactured by Tesla. The architecture of the ADAS sensor of this vehicle is domain centralized in the Tesla computer unit. The computer unit includes also infotainment function and radio frequency function like 4G LTE, Wi-Fi, and Bluetooth. On this page, we can see the different ADAS sensors used on the Audi A8. There are one night vision camera manufactured by Autoliv, one lane assist front camera from Aptiv, 2 360 degrees camera on the side mirrors, one long-range radar from Bosch, 4 mid-range radars from Aptiv, one LiDAR from Valeo, and also 12 ultrasonic sensors. There is all the type of sensors, LiDARs, cameras, radar, ultrasonic sensor on this car. As for the Tesla Model 3, all these sensors enable safety features like active lane and speed assist, collision avoidance assist, and also convenience features like adaptive cruise control and parking assist, and a traffic jam pilot. Some sensors, like the infrared camera of the night vision system or the LiDAR, include a processing board associated to them. The other sensors are connected directly to the active zFAS central driver assistance controller. The architecture of this vehicle is then a mix between distributed and centralized domain architecture. Now, a short focus on the Tesla Model 3 cameras and radar. In this slide, we can see some details about the Tesla forward triple camera. We can say that it is a simple design. Actually, not really simple, just because there is no computing inside. The computing is done by the centralized Tesla computer unit. The same CMOS image sensor from ON Semiconductor is used 3 times on the electronic board. And each image sensor is associated with a different lens module according to the range and angle of detection. The main detection has a range of 150 meters for an angle of 50 degrees. The narrow detection has a range of 250 meters for an angle of 35 degrees, and the wide detection has a range of 60 meters for an angle of 120 degrees. On the cross-section of the 3 lens module, cross-section that have been done by our laboratory, we can see that the build-up and the difference between the lens module to get several range and angles. Here we compare the architectures of the Tesla triple camera with the ZF SCAM4 tricam that can be found on the BMW X5. On the electronic boards of the ZF tricam, there are 3 image sensors from OmniVision, and also integrated circuit used for the processing functions. There are Intel Mobileye iQ4 system-on-chip processor, 32-byte MCU from Infineon, and 2 SDRAM memories from Micron, each with a capacity of 4 gigabit. This processing function explains the cost differences between the ZF tricam, estimated to $165, and the Tesla tricam cost, estimated at $65. Another interesting point of the Tesla Model 3 is that all the 8 cameras placed all around the car use the same CMOS image sensor from ON Semiconductor. Its reference is AR013680. It is neither the latest nor the most important, the most performant image sensor from ON Semiconductor, because its resolution is only 1.2 megapixel and it was released in 2015. Now, a few words about the only radar of the Tesla Model 3. Bought from Continental, the ARS-4B is a long and short-range radar released in 2016. On its electronic board, there is a complete chipset solution from NXP Semiconductor. There is the 77 GHz receiver and the transmitter, the voltage control oscillator, and the 32-bit MCU. All these circuits are from NXP. This radar is not an exclusivity for Tesla, because it can also be found on other cars like the Audi Q3, the Volkswagen Tiguan, or the Nissan Rogue. And at least 15 other vehicles use this radar. Now let's talk about the ADAS ECUs. This is an illustration of the Tesla computing unit. It is a liquid-cooled dual computing platform with both its autopilot and infotainment computer built onto 2 different boards in the same system. It is the same system electronic, and there is an infotainment ECU for the media control unit and the autopilot ECU. It is not two different and independent systems like in other cars. Here, we can see the evolution of the hardware versions from the first version in 2012 to the actual version, which is the 3.0 version. Thanks to the improvement of the hardware and software inside the Autopilot ECU, the processing power is now multiplied by 420, and the number of frames that can be computing per second is now 2,300 compared to the figures of the first version. We can also see the differences between the two last versions, the 2.5 and the 3.0. Redundancy functions are added in the 2.5 version, and the processing power is multiplied by 10, and the number of frames per second is multiplied by 20 in the 3.0 version. To compare precisely the hardware of the Autopilot ECU version 2.5 and the new version 3.0, we use the data supplied by our new online teardown service. It is called reversecosting.com. Since January, a new section was added. It is dedicated to teardowns and cost estimation of automotive electronic systems for applications such as ADAS, infotainment, telemetrics control unit, airbag controller, DC-DC converter, and also other applications. In the website, there is an interesting function to compare the high-resolution photos of the electronic boards side by side, and another function to compare the bill of materials. So, we can see that the electronic boards of the two last versions have the same dimensions, but the number of components increase in the 3.0 version. When we compare the chipset of each version, and particularly the processors, thanks to the high-resolution photos of the die, the measurements and the technical data available on the website, we can see that in the 2.5 version, there are 4 processors. One NVIDIA Pascal GPU, 2 NVIDIA Parker System-on-Chip, and 1 Infineon MCU. In the 3.0 version, the processor number is reduced with only 2 ASIC specifically developed by Tesla. Thanks to this evolution, the processor's footprint was reduced from 4,180 square millimeters to 2,800 square millimeters. But the processor dies area of the 3.0 version increased. It is now 611 square millimeters with the technology node of 14 nanometers instead of 16 nanometers in the previous version. Thanks to the improvement of the hardware and of course the software inside the Autopilot ECU, the processing power and the number of frames by second have been increased significantly between these versions. In terms of cost, the bill of materials of the hardware 2.5 is estimated to $795, and the 3.0 version is estimated to $635. So, we estimate that there is a cost reduction by 20%, even if the computing power was multiplied by 10 between these two versions. We also use the website to compare the active zFAS and the Audi A8 to the Tesla hardware 3.0. The active zFAS includes 4 main chips dedicated to specific functions. The NVIDIA Tegra K1 for traffic sign recognition, pedestrian detection, collision avoidance warning, light detection, and lane recognition. The Intel Mobileye Q3 for traffic sign recognition and 360 degrees camera imaging and processing. The Intel Altera Cyclone for object fusion, map fusion, parking pilot, pre-crash, sensor data pre-processing. And the Infineon Oryx MCU for traffic jam pilot, assistance system, matrix beam, and road graph. We can see that there is 2 times fewer components in the active zFAS than the Autopilot 3.0. For the bill of material cost, the active zFAS is estimated at $255 compared to the $400 of the Autopilot ECU board. In the zFAS, the NVIDIA chipset uses a 28 nanometer technology node. The iQ3 uses 40 nanometer technology, and the Infineon Oryx uses 65 nanometer technology node. When we compare the footprint of the processor, we can see that the footprint is slightly higher for the zFAS, but the total processor dice area is 30% higher for the Tesla Autopilot ECU. So, thank you very much for your attention. I hope this webcast was interesting for you. And now we have a short session to answer to your question.
Thank you. Thank you very much, Wilfried. Very interesting presentation. We will now going to the wrap up with the Q&A session. So we will answer as many questions today as we can, and we will follow up via email for all the remaining one. And I can see that we have a lot of questions. So maybe the first one will be for you, Kerik. What is the VCSEL percentage share in LiDARs against EEL?
Thanks, Cesar, for the question. So just to put things in context, so LiDAR, for LiDAR, we can use different type of light source. So as mentioned, EEL is a light source, but other type of light source exist. So there are VCSELs, but there are also fiber lasers. Edge-emitting lasers are widely used by LiDAR manufacturers, and because they are cheap and they are largely available from suppliers. So most of LiDAR manufacturers are using edge-emitting laser at 905 nanometer. And some others are using fiber laser at 1550 nanometer, especially for long-range application. And others are using VCSELs. So when you look at the LiDAR ecosystem, there are more than 70 LiDAR manufacturers. And we have seen that, I'd say, less than 10 are using VCSELs for LiDAR, either for ADAS application or for robotic application. Most of them are still in R&D stage, but some are already selling some products, like Auster is doing for robotic vehicles. And let's say the common point for LiDAR manufacturers using VCSELs is that most of them are developing short-range flash LiDAR. This is the let's say the typical type of LiDAR because of the output power of VCSEL, which is lower than the output power of edge-emitting laser and fiber laser.
Okay, thank you, Pierrick. One more question. One more question for you, Pierrick. Let's carry on with you. Why adding more sensors in ADAS vehicle? That's for the ADAS part.
Yeah, sure. So the main reason to add sensors in ADAS vehicles is, as I was saying, is to increase the safety of the driver and the passenger. So firstly, it's related to the AEB features to avoid forward collision. But you can see that OEMs are also developing features for to prevent reverse collision. And the reason to add sensors is to be able to monitor the surrounding of a car in every condition. So not only in bright light, but also in low light condition. And this means that not only traditional sensors like radar and camera will be used, but also new sensors like LiDAR or thermal cameras.
Okay, thank you. Wilfried, one question for you, please. Who is the supplier of the CMOS image sensors of the front camera of the Audi A8?
Yes, there is also an on-semiconductor CMOS image sensor. It is like for the Tesla Tricam. In fact, it is the same manufacturer, and in terms of chip, it is not exactly the same reference, but we have seen that the two components have the same die area and the same resolution of 1.2 megapixel.
Okay, and one more question, Wilfried. That's for the did the night vision camera preceded by the zFAS?
We are not 100% sure that the night vision camera is processed by the zFAS because there is also a dedicated ECU associated to the camera module. So I think it is possible that the processing is done by this ECU.
Okay, interesting. One more question maybe for Pierrick. Is Ethernet network already in use today?
Yes, Ethernet is already in use today. In fact, it was firstly used in 2008 for the OBD onboard diagnostic application. And since then, some OEMs like BMW have been using the Ethernet network for other functions like surround camera or infotainment.
Mm-hmm. Okay. One more question, Pierrick. Do you believe higher resolution imaging radar can replace LiDAR? That's an interesting question.
Yeah. It's you're right. Imaging radar are still in development today, and we think that we will still have, let's say, the three main sensors in the ADAS vehicle. So there will be camera and radar. Each of these sensors are continuously improving, and radar is moving toward high resolution to have a better vision on the vertical field of view. But we think that there will not be one, let's say, one winner of regarding the sensors, and it will be, let's say, there will be a redundancy. So we will need different sensors to have different type of data. so that the computing let's say the computing part can process or fusion all the data from the different sensors and have a precise view of the surrounding. So in the end, so just to summarize, so I do not believe that one sensor will replace another. It will be all the sensors will be complementary.
Okay, thank you, Pierrick. We still have some other questions, but we run out of time, so the webcast is now over. You will soon receive email with the link to the recorded session, and we will also answer the remaining question. So also, please feel free to share the presentation with colleagues. Please let me remind you that you can find all our reports on our website, www.i-micronews.com. Finally, we want to share with you a forum that we are organizing with the CIOE in September 10th in Shenzhen, in China. The Imaging and LiDAR for Automotive Forum 2020. The registration is à la carte, as you can attend the event online or on-site. Meet and discuss with the key players of the industry. You will find more details at the link provided. So do not hesitate to contact us if you have additional questions. You can find our contact details on the last slide of the presentation. Thank you very much, everybody. Thank you, Pierrick and Wilfried, and thank you, everybody, for joining us today, and have a great day. Bye-bye.